Hi, everyone. Can you hear us all right? Okay.
Yes.
Perfect. Thanks, Polly. So today, I'm very excited because we have a slightly different approach. So if you are not here in Athens, you may not have realized, but Neva, our teaching assistant this semester, she's been coming to every class and sitting here in Athens to help out. I don't think she has had a lot of work, at least as far as helping others out in class yet. But then one of my requirements for a teaching assistant is that they develop a lecture, a lab, and a full exercise. So Neva is a PhD student in our program here. She works with Dr. Lorena Lacerda, and she's using hyperspectral UAV-based remote sensing on her research. So she is our expert on hyperspectral, and she prepared a really nice set of slides and also a partial script and exercise for us to first understand hyperspectral data and then to do a full exercise on processing that data in R. I sent you all an email not too long ago, sharing with you the partial script and also the data for this exercise. The data is it is in our 03 data folder, I guess, or 02 data, one of the two, on GitHub. And because there were 3 layers of data that are part of this exercise, I just put them all under a subfolder called Hyperspectral. So you can get all them more easily. But make sure that you create that exercise on your side, 15_hyperspectral, create the subfolders, create the RStudio project, and then move the partial code into the code folder and the data into the data folder. And we're gonna first go through the lectures here, the lecture slides here with Neva. She's gonna teach us about the concept and the technology behind hyperspectral remote sensing, and then we're gonna do an exercise on processing that data. I guess something else I ask is, towards maybe, I think next week, I'm gonna ask you all to fill a student evaluation for this class, which for the most part is gonna be related to my teaching and my interactions with you, my skills throughout the semester. But if you have any notes about Neva's teaching as well, we always appreciate constructive feedback. And so if you have anything that you would like to add to that student evaluation as far as Neva's teaching today, you can do that as well. And I'll make sure to pass that on to Neva so she can get the feedback and improve for future as well. All right, before I turn it over to Neva, any questions about anything before we get going with hyperspectral? All right, I don't hear anything. So I'm still going to be here in the room. If anyone has any questions for me, I'm still going to be here and listening to you all. But other than that, I'm going to turn it over to Neva, who I'm sure is going to do a great job. Thanks, Neva. Welcome.
Thank you, Dr. Bastos, for the nice introduction. Hello, everyone. So I assume you already downloaded the PPT of today's lecture.
I have not shared it to them yet, but we'll do that right now.
All right. Dr. Bastos is sending you the lecture notes for today. In the meantime, I'm sharing my screen. All right. Can we see the screen, right? All right. Okay.
So I think we're seeing. So I'm seeing that the slides and comments below. Maybe I don't know.
Oh my goodness. Can I send the PPT?
I think
I don't know why, because I
is there a way that you can swap
just
this place?
just
I think that at least online, I think they'll be able to see the where is it and
it does.
I think Vivo is using.
Yeah, cross hyperspectral.
Yeah. So if you come here, let's see.
To share that PPT.
So this is what we're seeing right now. I was just wondering, there's a way that you can flip over there. Swap and see if you're breaking quickly. Let me try again. Yeah, this is I'm not sure. Oh, do you have the PDF? Maybe the PDF would work better.
Yes, I have.
Unless you have a lot of animations that the PDF wouldn't work.
Oh no, my animation.
Okay, so maybe if you
Dr. Bastos, for now, we can see the full screen.
Oh, you can see the full screen now?
Yes.
Okay. So maybe it worked, but
Right.
I think it worked. Yeah, so you should just go back to your PPT. Okay, I think we were sharing that. So maybe just, let's see. Okay, just have one now, right? Okay, so
While I'm sharing.
So I think what we can do is you can come here and present. Let's try again. Whatever, I think we had it right before. So there's a way. And maybe let's try this. And then see what happens if we do this. Okay. Aman, are you seeing that? Okay. Awesome. Good to go.
Good. Thank you. But it's showing.
Oh, it is showing.
Can I see? Oh, like this.
Yeah, maybe we can
Oh.
swap. Okay, online, is that showing full?
Yeah, now full.
Okay, awesome.
This is okay. Yeah.
Okay, yeah. Good to go.
Thank you. Thank you. All right. Welcome everyone. I just okay, just a heads up. Today I'm gonna teach hyperspectral how hyperspectral sensor is working, application of hyperspectral in precision ag, and different type of sensors in different platforms, and how we can extract information from hyperspectral images, and challenges, advantages, these things. All right. When we talk about hyperspectral imaging, one term comes with hyperspectral imaging, that is spectral imaging. So spectral imaging, we know from the name that spectroscopy and imaging. Spectroscopy is the science where we study about light, how light can divide into several how one light can divide it into several lights or several bands. We all know that we see white light, and white light is going to be combination of different kind of lights. And imaging gives us the whole scenario. So when we talk about spectral imaging, we always see these electromagnetic spectrum, because this is the main basic of remote sensing. We only see what we only see the things when the reflectance coming in visible light, right, from 400 to 700. But we don't see beyond this spectral wavelength, right. So when we talk about other spectral imaging like RGB, multispectral, hyperspectral, those are different because of their wavelength range in electromagnetic spectrum. So hyperspectral works between 250 to 15,000 nanometer. And in that wide range, it is divided into several bands, like UV light is coming from that range, visible, near infrared, shortwave, infrared, and so on. But in precision ag, we are not focusing actually in the broad spectrum. We only want to know what is going on in crops. That is why we are interested about visible light, because we all know chlorophyll. Because of chlorophyll, we see plant green. We are interested about near infrared light, because the internal structure of plant depends on internal structure of plant can be seen in near infrared range. And shortwave infrared, basically water absorbed in these region. That is why we are interested in these three regions. Okay, makes sense? All right. Now, not every sensor gives us the whole electromagnetic range. Not every sensor gives us that. Depending on our application, we choose sensor, and different sensor gives us different electromagnetic region information. So I work with head-wall nano, and head-wall nano works between 400 to 1000 nanometer, which means it gives us information about visible light and some part and near infrared light. Okay, I don't get any information from my sensor about shortwave infrared, but head-wall has another sensor which works with near infrared and shortwave infrared. That is a different sensor, and the application are different. Okay, makes sense? All right. Now, when we talk about spectral imaging, three terms come all along: RGB, multispectral, and hyperspectral. What is the main differences? So RGB gives us only 3 bands, red, green, and blue. Multispectral normally gives us normal or the sensors we work normally gives 5 bands, but some sensors give more than 5 bands. But let's say for simplicity, we are talking about 5 bands. That 5 bands, what are the bands? Red, green, blue, near infrared, and red edge. If RGB gives 3 band and multispectral also gives 5 band, then what is the difference? We don't need RGB. But the main basic difference between these two sensors, when we take images with our phone, it gives us RGB image. It has only one dimension, and it gives information about X and Y, the spatial information, X and Y. One dimension, X and Y. But multispectral, if it has 5 band, if it has more than 5 band, then a different, same, 5 or 10 band, same. That 10 bands give us 10, or that 5 different bands give us 5 different images. In RGB, the 3 bands cannot be separated, but in multispectral, we can separate, or we can see that this is the 5 different bands, 5 different images. All right. Now multispectral and hyperspectral. So hyperspectral image, let's say my sensor gives information in between 400 to 1000 nanometer. And another multispectral also gives information about 400 to 1000 nanometer. Both gives us information about same electromagnetic region, but their bandwidth are different. Their information is different. How it is different? That is the main difference between multispectral and hyperspectral. So when we get information from hyperspectral, its electromagnetic region is divided into 100 of bands. What is a band? We already know that bands is the difference wavelength, difference of wavelength. If I have 2 consecutive bands, let's say one band is 300 nanometer and my next band is 302 nanometer, then the bandwidth is 2 nanometer. Make sense? All right. So when we work with hyperspectral images, the whole region is divided into so many bands. So there is no gap. There is no gap of band. Every region has a band. But in multispectral, it doesn't give us continuous information. Let's say red band. Let's say red band has bandwidth from 500 to 600 nanometer. So in multispectral, that is one red band, and bandwidth 100 nanometer. Okay, 100 nanometer bandwidth, and the range 600 to 700. But in hyperspectral, the same range is divided into, let's say, 30 or 50 bands. So that is divided into so many pieces. Okay. Then move on. As we already understand the main theory behind hyperspectral images, we know that which information or how we can extract information from hyperspectral images. It gives us continuous information, continuous wavelength information. There is one truth, that every material reacts with light differently. When light strike one matter, it gives us electromagnetic wave, and that wave is true for that matter, and that is true, that is unique. That is true and unique. That one important feature makes hyperspectral unique from other spectral imagery. I want to make sure if anyone have any question or you guys understanding what I'm saying. Because I can't see anyone, so it's hard to, okay, move on. All right. Now, how we work with hyperspectral imagery in field or in real world. As I mentioned, that multispectral image, we can have 5 different images from one multispectral image. Similarly, from one hyperspectral image, we can have thousands of images. Saying that when we have one hyperspectral image, it has its spatial information X and Y, and all the bands are there on top of each other. And it makes hyperspectral imaging a cube. When we read paper, it always says hyperspectral cube. In the image, we see that one aeroplane is taking images from one field, and then we flipped the field, and the X and Y and all the bands are there. Then we divided the bands, and at the bottom, the bands are showing different reflectance spectrum. That is the main basic of hyperspectral imaging. All right. Moving on. Now we easily will understand the applications of hyperspectral imaging, as it can give unique spectral reflectance from each and every materials. From just seeing the reflectance, we can see which is soil, which is water, which is vegetation. From the image on the left, this is a land cover map, and from 3 different patches, we get 3 different reflectance images. All right. Not only that, not only we can differentiate different particles or different matters, from same type of matter, we can differentiate with hyperspectral imaging. On the right, it is showing there are 3 different plants. So first of all, from land cover mapping, we can differentiate soil, water, plants, or vegetation. On the right, we can differentiate different vegetation just looking into the spectral reflectance. All right.
This is something
Yeah, sure.
you mute yourself so I can mute.
Things.
Go on top, but we're screen share and use mutes.
Hey everyone. Just all right. Okay. So I just wanted to say here, I just updated the class website. So not EOC, but on the website. If you go there on the program in Precision Ag, there is a link for the PDF as a lecture symbol on the lecture for today. So just in case you want to follow along with the PDF and take notes, it is on the website right now. All right. Thanks, Niva. I'm going to mute here and then you can continue.
I just wanted to know if anyone works with hyperspectral or not. So I hope not. If you have any question, please feel free, because while I started working with hyperspectral, there were so many questions, because that was really silly question or very simple question, but it took me a long time to understand or to get the answer. So if you have question, just ask. I'm not anyone to judge, just ask. And maybe I'm keeping something which I know I don't need to share, but maybe it's new or something else, you can just ask. All right. Hyperspectral imaging is very well known or getting popular in food science, in precision ag, I didn't know any professor, but in food science, I saw several professors are working with hyperspectral imaging. One of them is working with meat, beef. So this is a lab-based setup. So the difference, the distance between the sensor and the target is really low, and they are trying to see the internal materials of that meat. I mean, like moisture, protein content, and other particle size, and so on, so that they can say how many days this meat can be stored, something. And on the right, there is another applications. It is also very popular to sorting, grading different foods according to their shape, and if there is any other foreign particles or not. They are using hyperspectral for that. Here comes our precision ag. So maybe you already can understand, or you can make assumption how these things are related to hyperspectral, and how using hyperspectral we can make things in precision ag. So first, monitoring plant growth. As I told, every materials react with light differently. When plants are small, they give one spectral spectral a reflectance curve. When they grow bigger, the curve changes slightly. Not drastically, but slightly. Then detecting stress. So we all know the basis of plant, that they have chlorophyll, and because of chlorophyll, they are, I mean, showing their greenness, and while they reflect green light, they are absorbing red light. So this is the main basic of plants, and I work with that basis. So in healthy plant, while lot of green light is reflecting, when the plant is sick, the chlorophyll content will not be same. The light reflection won't be same. There won't be same. And also in near infrared range, the internal materials of leaves, they will not react with light in the same way. So the reflectance curve will be different. And from there, we will know something is going on there. Stress, early symptoms of disease, soil texture and quality, it all can be explained by hyperspectral imaging. Okay, I want to mention soil texture and quality. So different soil has different texture. Clay soil has more clay, more water. Its reflectance curve will be different from sandy soil, because sandy soil has less water in it and it is shiny, we know, so its reflectance super different from clay soil. Those are the bases. All right. Now here comes hyperspectral platforms. So yes, so hyperspectral sensor can be mounted on different platforms, but this slide specifically is important, I don't know, because I recently come to know about this difference. So I'm showing here a green seeker handheld crop reflectance sensor. Is that a hyperspectral sensor? No, because it only gives us reflectance. So it gives us just number. Maybe, yes, there are lots of bands, but not image. It doesn't give us image. It just gives us number. in red band, what is the reflectance value, in infrared band, what is the reflectance value, which is totally different from hyperspectral imaging. So on the right, I put one sensor that to show that one sensor can be mounted on different devices or different platforms. So this sensor, I don't know why I missed one example. This sensor can be mounted on, what is that? Microscope. So to see or analyze small things in microscope, we can install this sensor. We can install this sensor in lab setup, also outside, but it is not it can't be mounted on UAV. So that is the difference. So we can mount it in outside, but in a proximal setup, so the distance between the target and sensor will be low. All right, there are different hyperspectral sensors. All right. Satellite, yes, like multispectral, hyperspectral also are mounted or installed in satellite. We already know the advantage and the limitations of satellite, but I want to mention here the examples. I put three examples. One, Hyperion, although it is already shut down. Yeah. Then Proba Chris, Planets, Tanager. So these hyperspectral satellites give us more bands. I didn't put the band number, but the reflectance, but the spectral resolution, those are really low, 10 nanometer. While in multispectral sensors, we see the spectral resolution is really high, although it is in satellite, but as it is hyperspectral sensor, the resolution is really low, only 10 nanometer. That means we can get information every 10 nanometer wavelength region. And the resolution is really high, 30 meter. The most popular platform UAV in precision ag, as we are in this class, I believe most of us work with UAV. I work with two sensors. One is Headwall Nano and Resonon Pica L. So those are two sensors name, but the company, they make different sensors according to customers' application or customers' need. So Headwall, as I mentioned earlier, make two nano and micro. Their wavelength region is different, and sometimes their length is different, their focal length, everything is different. In Resonon, if we search Resonon, there will be 10 sensors. And all the sensors, resolution wise, spectral resolution wise, their length wise, they are different. And between two sensors, I'm working with Hyperspectral Nano gives really high resolution spatially. It gives 5 centimeter of spatial resolution. That means really detailed information I get from my Headwall sensor. Resonon gives a little bit coarser, but it's also really high, 50 centimeter. Okay, and their spectral resolution is really low, 2 point something. So in one image, I get variation of wavelength only 2 nanometer. This is the 3 most popular hyperspectral sensor in literature. While I read literatures, I see 3 popular sensors. And as I told, that all sensors has different versions, different specifications. And this is the last one, close range hyperspectral platforms on the left. That is a handheld sensor. So what I was showing green seeker give us only the spectral value, but this leaf spec, it gives us image. I don't know if it is commercially used or not, but I found it from University of Purdue. Some professors are developing this and they are working with this sensor. And in horticulture also, one professor is working with this sensor in greenhouse based. And this sensor can be used in greenhouse and also in outside, but we have to use our hand. And on the right, that is another closed range platform that is lab based, but it also can be used in outside, but we should have a platform so that platform will move and it will take images in a very close range. Okay. So I had, okay. All right. Everyone understood everything. I wanted to ask one question here, I forgot. All right, we are done with our platforms. Now light source. RGB, hyperspectral, multispectral, all are which sensor? Passive sensor, because they need one light source, which is sunlight, obviously, but it can also work under halogen light, LED, and thermal. I didn't see much literature about LED and thermal, but in greenhouse or lab setup, halogen light use a lot. All right, moving on. So if this UAV setup is more or less same, because in multispectral also we need one calibration board, calibration board, sensor, and gimbal. But this laptop, I'm not sure I saw any laptop connected with multispectral in field. So this setup is for UAV working in the field. All right. So what is this calibration term? Hyperspectral works as it needs light source and it should be sun in outside. It needs to know if it is collecting the actual reflectance value. That is why this calibration term. So it is a big cloth colored with white and also ash, but I don't know the use of the ash versions. So I have two calibration tab for two sensor, Resonon and for head wall. One is colored white and ash, another one is colored white, ash, and black. So while I calibrate, I only use the white portion. I'm sorry that I don't know about the other color. So why we use calibration tab? When we collect images, it gives us reflectance coming from the plants. But that reflectance depends on sun too, the illumination. So when we have a white surface, that white surface gives us maximum illumination. So we know the maximum reflectance on that specific day. And when we get reflectance from our target, let's say vegetation, we can subtract from maximum from that day from what I am getting, because that illumination will not be universe. It would be universe for only that day, that location. So that is the use of calibration tab. And we have to have calibration tab on the field when we are collecting our UAV data. In the image, we have to see that the tab is there, and that is when we process our images from our big field. We have several images. For hyperspectral, for 20-acre field, we have maybe 100 images. So we need to stitch all the images and all the images for processing. The first image we have to process, that image has the tab. All right. Then gimbal, we all know that gimbal helps us to stable the sensor, because in field the UAV moves a lot. We can't we can't control wind and everything, but at least the gimbal helps to stable the sensor. It always looks at the nadir position sensor. And finally the laptop. Here is another big difference, hyperspectral and multispectral. Because I don't know, I saw multispectral just takes images, but in hyperspectral, it never starts if the illumination is not high enough. So before start collecting data, we have our UAV ready, our sensor attached, and our laptop, and we connect our sensor with our laptop, and there is a software we have to see if everything's fine. We have our what is that we play with the controller, but that is one thing. Controller is a must for the UAV, but to start the sensor we need that laptop, and in the laptop we have our software which make sure that yes, today's sun is high enough to take images. Then our sensor starts. And what if at the very beginning the sun is bright enough to start the image, start to take images, but in the middle there is big cloud, the sensor will not take any images.
But so there's a question in Tipton. I mean, you can just unmute yourself, or does not unmute yourself, or you can just ask them if they don't answer, but go ahead and answer the question.
Yes, I have a question.
Yeah, sure.
Yeah. How often do you need to calibrate the hyperspectral sensor? Do you, for example, are running a flight on a big field that will take around maybe 30 minutes, and considering the real time change, the clouds are going to change, the light intensity is going to change. How often do you need to calibrate?
Thank you for your question. That's a great question. So calibration needs just beginning of the flight. When we are starting our flight, we need to calibrate. Okay, so the calibration and the what I was talking about, the laptop, those are different. Calibration tab we will leave it in the field, and we have to take image of that calibration tab. That is one thing. And to start the sensor, we need to move our sensor towards light, so it can see how much light is entering into the sensor, and then it will start. But we never know if it is taking images or not. We can see from the controller that the UAV is moving, but we don't know if it is taking images or not until we are stopping our flight and connecting and start extracting data. So when there will be a cloud, or you can feel it after seeing that it is not the light is not enough, then you have to stop your UAV right there, and then when the cloud will pass, you will start your collection again. Make sense?
Yes, I have a follow-up question.
Sure.
Do you have an instrument that can measure the intensity of light? Like how much light do you have? How do you know you have enough light?
Yes. So that will tell that software in the computer in the laptop when we will start our sensor. Start our collection. First, we have to connect our sensor with laptop, and then there are some steps. We have to follow all the steps, and the most important steps is that when we will move our sensor to our light, to our sun or outside light, and the light will enter into the sensor, there is one threshold value, 3000 K. Okay, 3000. I only remember the number 3000. So when we have that threshold value, only then the sensor can start. So there is a threshold value to start the sensor. And it all happens before collection and to just start the sensor. Polly, are we good?
Yes, we're good.
All right. So, and for this head, I'm showing here. Okay. There is one more thing. I'm showing here resonance Pica sensor. I didn't fly this sensor in the field, but I flew head wall. So in head wall, the threshold is 3000 K. I am sorry that I can't say what is the K means, but it should be different for other sensor because every sensor is different. Okay, so this is the main thing. Thank you for your question. All right, so when our sensor starts, then we will take our UAV to the field and then we will start flying UAV. And when there will be cloud, we have to stop because it happened with me. We collected data, we came to lab, and then we saw there a big chunk of field I don't have any image. All right. So this is my UAV, DJI Matrix 600 Pro, and one of my sensor head wall. I think we already know about sensor and UAV because a lot of sensor are compatible with a lot of UAVs. So both sensor head wall and resonance are compatible with this DJI Matrix 600 Pro. All right, so we start our flight. We collected data, then we it could be in the field or after coming to the lab. We extract the images in another computer, not that laptop that was used in the field. That is a really different laptop. In where we are using a different software just to fly the UAV. Now to process, we will be using another software. For hyperspectral, like for multispectral, as far I know, Pix4D works with Pix4D works for different or a lot of multispectral software, multispectral sensors. So we will have different sensors, but all images are same. So we can use only one software to process. But for me, as I am working with two sensors, two different sensors work with two different software. And their extensions little bit different. Their processing is different. So here I am explaining head wall software. Yes, head wall software, head wall sensor. And the sensor I'm working and software I'm showing here spectral view. In hyperspectral, it is sophisticated, or we have to be very careful with the extension, because the file, most of the time, same file, different extension says different things, which is true actually for other things too, but in hyperspectral it is sophisticated. So we came to the lab and we extracted all the data we have got into processing computer. Let's say, yeah, processing computer means lab computer, because hyperspectral is really hard to work with personal laptop. I can't process hyperspectral data in my laptop. I have to have a very powerful computer. In there, all the image cubes are there. Now, I can see the image cube. But to see the image cube, I have to do something. When I extract data from the sensor to computer, I can't see first thing, but later after doing something, I am not going to explain that. But if anyone have interest or anyone wants to work with, ask me. So I'm explaining from here. So at a certain point, we can see the image cubes, and that image cubes are like RGB images. Like here, I'm showing one image, and we can see the raw hyperspectral cube, which is a little bit shaky. Okay. Now, this raw cube, we have to do several processing to have our actual values. Right now, this raw cube doesn't mean anything, and I can't work with this. And this is one of the most challenging tasks to pre-process hyperspectral images. Then I have to do my radiometric calibration. What is radiometric calibration? You already remember we used one calibration term in the field. Okay. Before going to that calibration term, we did another calibration thing. What we did, while I was connecting that sensor with flight laptop in the field, we had to take one image with the sensor. What is that image? Sensor has a cap, because camera. Sensor is a camera, right? So the camera has a cap. We have to take one image with that camera and do it with that cap on. That means there will be a black image, just nothing, just a black image. Okay, so this is the first part. To cancel noise, we do that. This is the first part. We do one calibration. Why we take that black image? Because every sensor has their own limitations, own noising system or something. So when we take image in outside, there are also lots of noise because of environmental thing and everything. To get actual data or absolute data, we have to cancel noise coming from the sensor. So when we take the image with the cap on, that image will have noise coming from the sensor. Then I will have image from the field. When I will subtract that image from this image, I will have the noise only coming from field. I subtract the noise coming from the sensor. Okay. Now, when I have that image, now I have to subtract another thing, which is that white reference. So now I have one image which doesn't have any noise coming from sensor, but I don't know the illumination on that day. So from that image, I told you when we will process our data, first thing we have to find out the image with that TARP. So that TARP has reflectance or radiance, 100% reflectance, sorry. The TARP has image 100% reflectance on that day, and my image has reflectance coming from my target. When I will subtract that, I will have reflectance coming from only that target, only from my vegetation. Okay. All right. So that is radiometric calibration we have to do in hyperspectral imagery. This is, I think, common in satellite sensor also, but do we need to do that in handheld sensor? Maybe when we are working in outside, but in greenhouse we don't need to do that calibration because the light is same for all the vegetation. But in outside, light is fluctuating. Okay, so if we see the reflectance curve here, so the first on the left, that is the reflectance coming from raw data. Then we did another calibration with the cap on, the reflectance changed, and finally we got our true reflectance. So from that true reflectance, if we know the characteristics of plants, that plants have a peak on green and ditch on blue and red zone, and the peak in near infrared, this is the true reflectance coming from my vegetation. Okay. All right. So when we have true reflectance after doing the calibration, this is our true cube. So we can see the difference between the two cubes. One is shaky, which is not calibrated, and on the right, that is corrected cube. Okay. All right. Now, when I have one cube which is corrected, I have to correct all the cubes, all the images. Now, after correction, I have to do second correction. So first calibration was radiometric calibration. Now I have to do geometric calibration. What is geometric calibration? I have my image, cube. How can I know that cube is belong to that place, specific place in the field? So in that term, we will do geometric calibration. We also can say it orthorectification. To do that, sometimes we need a digital elevation model, which is a different thing. I don't want to drag here, but we need something to say the software that this is my elevation or elevation model. So this is the place, and put that image into this place. Okay, geometric calibration. All right. Now, this geometric calibration is the trickiest part in hyperspectral data. Why? Because drone doesn't go smoothly. If it works like aeroplane. In aeroplane, or what is that? Unmanned aerial vehicle. There are three kinds of distortion. One is roll, when the aeroplane is moved like that. One is pitch, and another one is yaw. Because of these three direction of distortion, our image would be different. The image will not be exactly horizontal, or exactly, it won't fit in that location. We have to have correct that row, pitch, and yaw. And this is the hardest part, because, oh my God, I don't want to talk about that. Okay. So after geometric correction of one cube, we will do it for all the cubes. Then we will stitch all the cubes to get the whole field image, and we call it orthomosaic. In multispectral, we also do that orthomosaic. So in orthomosaic, I put there two images. One is all the images I took there, and finally the image we see. So that stitched image is header file. We can see that in the software or Google Earth, but we cannot work with that. So different softwares are there. Different people feel comfortable in different software and they work differently. For Hyperspectral, a lot of people work with, I forgot the software name. All right. Okay. But I prefer to work with QGIS, because if I take that header file to QGIS, I can have one raster file. And from Dr. Bastos' class, I really feel comfortable with raster file, .tif file. So in that raster, I have my 270 bands all together. Now I can extract data and I can work whatever I want to do. NV. People work with NV software because it is comfortable with hyperspectral sensor or hyperspectral data. But I work with R. I'm comfortable with R. But to get to R, I need QGIS one step to extract. To make that raster from that orthomosaic. To get the raster, I need QGIS. But it is by my choice. It can be done in different ways. All right. Now I have that raster file and I'm good to go. When I have raster file, I can do whatever I want to do. So it is really easy. Anyone has any question? All right, thank you. So so next, my target is to extract the spectral information, right? So then I can do it in R, but I want to mention one thing here, plant cell segmentation, which can be really easy for multispectral sensor, multispectral images, but in hyperspectral, it is tricky because there are lot of bands. If we just extract one single band or 2 or 3 bands and segment, it is easy, but to segment all together, it is really hard, and it is not same for all stages. Like in early stages, the plants are really small. We only can see soil. In later stage, we can only see plants, but no soil. There are different methods, different machine learning algorithm. But here I used NDVI for one of my stage to segment plant and soil. And the main basis of this segmentation, because we see from the image that the reflectance coming from soil, it is almost uniform, but reflectance coming from vegetation, that is different from soil. So these unique characteristics help us to segment plant and soil, but it is not straightforward. We have our limitations, whatever. So today we will be doing this extraction. So now I have my raster data. So in this raster data, I have my soil pixels out. Now how I am extracting the values? Now I need values and a table. That is easy. So this is my plot, and inside plot I have another circle because I collected data from that circle. I have one point and collected multiple samples around that point randomly. That is why I want to show both of them. And then in R, just extract. and all the values there. So today we are gonna do that in our script. And when we have our table, now like any other variables, we can use our hyperspectral data variables. And there are some possibilities. We can do cluster analysis because we have so many bands. Like for my sensor, I have 270 bands, means 270 variables. So, and some of the variables are really close to each other. Their characteristics are same. So we can do that cluster analysis. We can do correlation analysis, which bands are correlating with my target variable. Then we use machine learning algorithm to select specific narrow bands for my target. We can do model. Obviously, we can do vegetation indices. So there are some benefits in of hyperspectral imaging in precision ag. That is non-destructive, environmental friendly, and cost. Yes, it is costly when we buy the sensor, but if we just buy sensor once, then we can use for several research, and it is precise and rapid. Yes, we have so many challenges. It's costly, and computational cost is really high, calibration needed, and it takes too much time. Lot of bands, lot of dimensionality. We have to do higher, higher machine learning or deep learning method to analyze our hyperspectral data. Bands correlate, and there are atmospheric disturbance, as I mentioned. If there is not enough light, it will not start. And I mentioned UAV. For satellite, there will be more atmospheric disturbances. There will be gases, there will be cloud, and everything. And this is the flowchart I wanted to show. And there are some resources. There are a lot more resources. If anyone has interest, I can share. And thank you. I took a lot of time.
Sorry, just a quick question. Could you go back to the workflow and just kind of like go over it and especially mention what parts of the workflow we're going to be working on today? Because definitely we're not going to do the whole analysis today, just parts of it. So if you can explain to us.
Sure. Just checking time. Okay. So this is the flowchart, pre-processing and post-processing. Although it is different, when I have data, I have pre-processing and post-processing. But in some literature, the processing during flight, they call it pre-processing, and after collection data, they call post-processing. But to me, I define it like that. So we collected raw data from sensor to our working computer, then converted the radians. As I mentioned, with the white reference, we converted the radians. Then from radians, we converted the actual reflectance value. Then we did ortho rectification of one single cube. What is geometric calibration? I wrote it wrong here. It should be geometric calibration. And then we stitched all the images, which is multi-ortho. And after doing the pre-processing, we will do our post-processing. We will convert the mosaic of whole image to raster. And from that raster, we'll extract band. This is one step today we are going to do in our coding. So we will extract band from image to table. Then we will do a simple statistical analysis. And also we will calculate one vegetation indices. And we will see in there how hyperspectral is different with multispectral. And in statistical analysis, we can use another variables like environmental variables. Then we build other models, but we're not doing that. We will just extract our reflectance values. Then we will calculate vegetation indices, and that's it.
You can check if anyone has any questions at this point.
Yes, if anyone has any question, because I guess we were gonna have a quiz, simple quiz. No question, right?
All right, so I guess we can go ahead with the quiz. I can make that visible here on our side.
All right. So in ELC, there is a quiz. It will take just 2 or 3 minutes, not hard, just the basic concepts. And if you are done with your quiz, you can take some time for a break.
I want to confirm that you can see this quiz number 8. Hyperspectral. Not yet?
Yeah.
Okay. So you can say that, so the quiz is available. You can tell them that we're gonna have 7 minutes. Within those 7 minutes, they can do the quiz and then take a quick break. And then we'll come back to the quiz.
All right, so let's start your quiz, and if you are done, you can take a little break. So I'm bringing the stopwatch of 7 minutes. We'll start our script after 7 minutes.
If I ask you just see if you can see this.
Oh. And Luke, can you see your quiz?
Yeah, I can see it.
All right, good, thank you.
Well, but maybe somebody asked a question. But you can just close that X and return a forward. No. Maybe not. I thought 15 had those. I think it's frozen on that side.
Again, I hope you already got all the data and script. If everyone is ready, we can start our coding part. So today's project is 15 Hyperspectral. And I believe you already have your project and data code set. So here, as I mentioned, that we will be extracting only reflectance values from the image. So here I put some introduction that we collected hyperspectral imagery from a 19-acre farmer's field from Peanut in Tifton, and the field is divided into 21 plots. So in farmer's field, there was no plot, but to ease our analysis, we are dividing the fields into plots, but there is no actual plot. But we will be dividing in our images and extracting information from the plots. And in that plot, why we flew hyperspectral? Because we want to see if there is any aflatoxin available or not. So we will be analyzing our vegetation, and we will be collecting field samples. I mean, lot of another variables like chlorophyll value, peanut pod size. Peanut pods, and some of the pods maybe have aflatoxin, and we will send that peanut pods into laboratory, and we will get the actual values, aflatoxin level on that peanut pods, and we will be using that as our ground truth data today. All right. All right, so here we already used our spectral view software. Then we did our radiometric calibration, our geometric calibration, and then our orthomosaic. After getting our orthomosaic, we put our image into QGIS, and we got our TIFF file. That TIFF file has 272 bands. And we also have our field boundary. So in this lecture, in this lab, I'm not bringing my field boundary because that doesn't make sense. I only need my plot boundary. I will be bringing that. So this is learning objective. We'll learn about hyperspectral data. See the reflectance variation in different bands. Not all the bands will give us same reflectance values, no. And then we will try to extract reflectance values from our image layers. We will play to combine some of the bands to get vegetation indices. And finally, we will identify which vegetation indices actually best to predict aflatoxin values. All right. First, let's call all the libraries. Then I'm sure all of the libraries you used before. So now I will be calling my hyperspectral file. I hope you don't have that chunk, right? Do you have, Aman? No.
I'm going to share. You can tell them that you didn't share because it was
already, yeah. Yes. So you don't have to do coding in this part because this is raw hyperspectral images. What is that? Okay, I'm showing you. So this raw hyperspectral image, it is really heavy and it takes 2 to 3 minutes to load. That's why we didn't want to share this file with you, and it's hard to upload in GitHub maybe. So what is this raw hyperspectral image? It is the exact image what I got from QGIS, that my TIFF file with all the bands. This is a raster, but I believe in class you learned about raster function and also star function to work with raster data, but I prefer to work with Terra library, because in Terra library I can have that function rast to read my raster file, which has 270 bands all at once. So this is just one file. In dimension, we see that it has 272 number of layer. Its resolution, maximum minimum value. So this is the reflectance values. Now, so I want to bring this image to remind again why we're doing this, because we want to play with reflectance value coming from plants, not from the soil. That is why I want to eliminate all the pixels, that all the reflectance value coming from soil pixels. So after removing soil, this is my hyperspectral image. Segmented. So this is my segmented hyperspectral image, and this layer, what I'm trying to bring this, because if we see the maximum values, I mean in every band, the reflectance values are lowered here. Like in segmented image, my value is 0.21, but when I have my image mixed with soil, my reflectance value were higher for each and every band, which was not going to give me actual reflectance. All right. Then move on. Now, there is one more thing. I can show you all the bands here, but it will take a lot of time. One of the most challenge working with hyperspectral is data value. It has a very high amount of data, lot of bands, and very high resolution, spatial resolution. That is why it contains too much data and it takes too much time. That is why I want you to start coding with me from here, because in here I resampled my spatial resolution. So we are starting with Rust function, and we are calling the data layer, which is resampled segmented hyperspectral.
Can you just clarify that only have, like that's the first one?
All right. So you have this file, this data. You have this TIFF file, resampled segmented hyperspectral, resampled seg HSI TIFF. you all should have this file. So you can call that file here, and we can start our coding from here altogether. All right, are we good? All right. Then, if we see the difference from my previous image and previous image and this image, because it has high spatial resolution. Previously it was 5 centimeter, now it is 5 meter. That means a very big amount of land is covering, and in that very big amount of land, pixel, I mean that very big pixel, there are difference of reflectance value, which was 0 minimum previously, because I have a very small pixel, and in there minimum 0, maximum was 0.2, but now the pixel is really big, and minimum maximum varies. All right. Okay, so I have my hyperspectral TIFF image here. Why I didn't call summary? Because if I call summary function, it takes too much time. But not for now, maybe because I already coarsened my data, but still I don't believe that. That's why I'm just calling the variable name HIS resampled. All right, then moving on. Now I have my hyperspectral TIFF file with 272 bands and the UTM zone 17, which means it is a projected raster file. Now I want to see some of my bands. That is why I want to plot my hyperspectral data. So if we call plot, I'm not sure if we can see. Can we see in Tifton? Okay. All right. So here I plotted some of my bands, 16 bands, first 16 bands. I have so many others, but in 16 bands, we can see that the reflectance value, we are seeing here reflectance value. The reflectance value has variability. Here 0.025, maximum, minimum 0.01. Here minimum 0.08, maximum 0.018. So there is variability. Okay. Now it's time to call our plot. As I told in Dr. Basus's class, we call the field boundary, but here I'm just calling the plots. Here is one difference, because we used SF, but sometimes I use stread. They are same. Read SF. Instead of read SF, I am calling here stread, but both are same. So I'm calling my plot is in data folder. Inside plots, I have the sampling points shapefile. Depth 7 sampling point shapefile. All right. This is my plot. So here one thing. This is my sampling points. If we see that the geometry type is point, because we selected those points, 1 point in each plot to collect our data, but we collect data around the points within 5 meter. Yeah, randomly. That is why now I want to make a buffer of 5 meter around that point. And I'm sure map view, here we can see the plots. Okay. This is my points, not plots. Yes, this is my points of my plots, from where we collect our ground truth data. as I mentioned that I want to make a buffer around that points. I'm sure we already know how to make a buffer. So first, then from that point, I want to make a buffer. Buffer. Five. And if we see the coordinate, it is WGS 84 because my points were made in WGS 84, but now as my TIFF file is in UTM, I want to make my plot buffer in UTM. Transform. Here I did one mistake because I can't do a buffer in WGS. I have to transfer it first. As Dr. Batus mentioned, it is a distance-based calculation. I have to change the CRS first, then make it buffer. All right, let's see if it works. All right, so it worked. It made a buffer because previously it was point, now it is a polygon. And my projected CRS is UTM 017. All right, if we map view. Okay. All right, next. As I'm working with Terra package, when I'm calling my raster, it is. Yeah, sure.
Yeah, there's a question.
But why did you use additional 5
who
meters?
has any question?
Yes, I have a question. Why did you use the distance of 5 meters for the buffer?
Hello?
Can you hear me?
Yeah, sure. Now I can hear you.
Okay. I was wondering why did you use a distance of 5 for the buffer?
All right. So I mentioned first I call the points from where we are collecting. We are supposed to collect our sample, but we don't collect sample from one point. We collect sample around the points, but within 5 meters. That's why we want to make a buffer of 5 meters. Make sense?
Yes.
So there is one point and we collect randomly our plant samples randomly around that point, but within 5 meters. That is why while we analyze, we make that buffer of 5 meters. Make sense?
Yes, thank you.
All right, thank you. Good. Okay. Oh, all right. Good. Thank you. Thank you. So as I mentioned, I'm working with Terra package, and in Terra package, I use Rust function for raster file, and to work with that raster package, when I'm pulling my vector, it should be called as a vector function. So my SF is now a vector object. So what was the name of my buffer? Plot buffer. So now plot buffer is a vector object. Here I have.
I think this is probably a good time for us to start because it's already 4:01. We can tell that to them, and then we'll continue on Thursday with doing exercise.
All right.
I'm gonna open the next one.
All right. Okay. All right, guys. It's already 4, so we are thinking this is a good stopping point. So we can finish the script next Thursday. And in the meantime, if you have any question or anything, you can just ask and.
Let them know that I just want the issue.
All right. So Dr. Bastos already opened the issue for today's attendance. You can just claim your attendance and leave the class. Thank you.
Thank you.